Alright, so this is part one of how to prepare Kraft Cooking Liquor. Specifically, we'll be talking about sodium hydroxide and sodium sulfide. The only difference with a soda cooking liquor is the lack of sodium sulfide. Alright, so let's begin. So in Kraft Cooking Liquor, it's an aqueous solution composed of sodium hydroxide and sodium sulfide. Those are the two active components. Now I'm going to write this down. The writing tends to lag a little bit, so bear with me. So let's review the stoichiometry. If we take sodium hydroxide, dissolve it in water, we get 1 mole of sodium and 1 mole of hydroxide. If we take sodium sulfide and dissolve it in water, you get 2 moles of your sodium, 1 mole of hydroxide, and 1 mole of hydrogen sulfide. So we specify the strength of our cooking liquor by terms of effective alkali and percent sulfidity. Okay, so our first equation is going to be the effective alkali. It's equal to the concentration of sodium hydroxide. Now I'm going to drop these brackets here and get lazy later. Plus 1/2 the concentration of sodium sulfide in solution. And we express all of this in terms of Na2O, and I'll explain that in a different video. So this is your equation 1. We're going to refer back to that. Equation 2, sulfidity, is expressed as a percentage of Na2S in solution. So percent S equals the concentration of Na2S over the total concentration of active components. So that's the concentration of Na2S plus the concentration of NaOH. And this is equation 2. Okay. So we're going to do an example problem here. We're going to prepare a cooking liquor with an active or effective alkali of 15%, a sulfidity equal to 25%, and we are going to treat 500 grams of wheat straw with this liquor, and we're going to produce 1 liter of cooking liquor, which we refer to as white liquor in this problem. It's a good habit to get into is to write everything you know out. Okay, so step 1, you're going to write everything out. Our percent effective alkali equals 15%, so effective alkali equals 0.15 times our oven-dried biomass, which is 500 grams, divided by 1 liter. That's the total solution we're going to make. We multiply that out, it equals 75 grams per liter as Na2O. So that's step 1. Step 2 is we're going to determine the target concentration of sodium sulfide in solution. So we're going to rearrange the equation 2 that we just prepared and get Na2S on one side of the equation, and then we'll solve for Na2S. Okay, okay. So step 2. Na2S, the concentration of, equals your percent sulfidity times your concentration of NaOH plus your percent sulfidity times your concentration of Na2S in solution. And we want to get to Na2S and NaOH on opposite sides of the equality. So rearranging Na2S minus percent sulfidity times the concentration of Na2S, and as you can see, I've dropped the brackets, equals percent sulfidity times the concentration of NaOH in solution. I'm going to pull Na2S outside, parentheses, times 1 minus the percent sulfidity, equals percent sulfidity times NaOH. Now we can rearrange equation 1 and then substitute in the NaOH in this equation and solve. Okay? So let's rewrite Na2S times 1 minus percent sulfidity equals percent sulfidity times the effective alkali minus 1/2 Na2S. That's substituting in for our sodium hydroxide from equation 1. Okay. Now we still want to rearrange and get Na2S on one side of the equation, so Na2S times 1 minus the percent sulfidity is equal to percent sulfidity times your effective alkali minus 1/2 the percent sulfidity times the concentration of Na2S. Na2S times 1 minus the percent sulfidity, and we're adding percent sulfidity 1/2 times the Na2S to either side of the equation. Okay, and pulling Na2S outside of the parentheses, and that equals your percent sulfidity times your effective alkali. Divide by both sides of the equation, and we get Na2S equal to our percent sulfidity times the effective alkali over 1 minus 1/2 times the percent sulfidity. And this will be our equation 3. Alright. This is the end of part 1, and we will solve for Na2S in part 2.